There we go. Okay, so some people are going to be missing out on the context, but okay. So anyway, the three partition problem is going to be the problem where you split into three sets instead, right? So X, Y, and Z. For those of you who are tuning in, I've just started. I'm just doing a reduction from partition to three partition. I'm explaining three partition right now. Okay, so three partition, right, says that I need to split this up into three sets. So when I say a three partition, right, what it means is that again, right, you partition it to two elements. This time you partition it to three, right? So these X, Y, and Z do not share items. All right, so you could have, for example, AI is equals to 5, and let's say like AI, like let's say AJ is also equals to 5, right? But so you can have, like, for example, a 5 here and a 5 here. That's fine, right? Like this is AI and this is AJ. That's completely fine, right? But what I'm saying is that, hey, okay, so like, this is the point I'm trying to make is that, again, all X, Y, and Z should not share elements, and X, Y, and Z should make up A. Okay. So by the way, all the problems that I'm showing you today, right, I've literally just solved yesterday. So I'm just going to walk you through my thought process. Like, so in other words, if I were in the exam now, this is what I should be thinking, right? Or this is what you could consider thinking, like, like something along those lines, right? And of course, the three partition problem is the same thing. You kind of want set X to equals to, the sum of the items in set X to be equals to the sum of the items in set Y to be equals to the sum of the items in set Z. All right. So at first glance, it doesn't seem like there's an easy way to do this reduction, right? Like how would you take this set A and construct some other set, perhaps like A prime or whatever, such that if this was two partitionable and then this is three partitionable. Okay, so the intuition here that I had was kind of like trying to remember how, okay, so if you try to do a reduction, you're like, when you do a reduction from the first problem to the second problem, you're kind of trying to say that the second problem really does solve the first problem, but maybe with some extra steps, right? Like if you remember how we did like the partition problem to the splitwise problem a few weeks ago, really what happened there was just, like us saying something along the lines of, hey, the splitwise problem really actually, just is just solving some version of the partition problem, right? That's what we were going for, right? And I think we can go for the same thing here. Okay, so let's just say for now we know what we understand. We understand that we need to take this set A1 to AN, right? And we need to output some other values B1 to BM. Right, I put M here because I don't know whether I need to, like, whether the set is going to be the same size, right? So what I'm saying is that if I take the items from the original set and all of it, like I'm trying to like morph it into something else, such that if the original one is two partitionable, if and only if the next one is three partitionable, right? Like I don't know whether I need to keep the same amount of elements. For all I know, I need to like pad some more elements, right? And it will actually, spoiler alert, it will be the case that I actually have to. Okay, so what was my thought process here? I was thinking to myself, okay, so let's try the simple things first, right? Like, like we can, if the simple things don't work, we can panic later on, right? Or maybe try a different question in the exam. I couldn't because I had to solve it for you guys. And just look at this and think to myself, okay, what are some straightforward things we can do here, right? Like, should we just copy every element twice? Well, that doesn't seem to work, right? Like it will work if this was 4 partition, but not 3 partition. Right, and if you remember, like there's this observation that I love to make. It's always very useful. The observation I always make is that, hey, saying something is two partitionable is the same as saying I could find some subset, right? Such that if I sum the items in the subset, it's just, it is just the total sum of the elements over 2, right? It's always just S over 2. Always, always, always. Right? So okay, fine. So the thing here is that we can make the same observation here, right? We can like, I thought to myself, all right, so if these three things are equals, it must mean that I can find some subset. It's actually more than that, right? But it means that I can find some subset, right, of items such that if I summed across it, it should be equals to S over 3, right? And then I should be able to again find some other subset after that as well. If I sum across all the items there, it should be like S over 3, right? Okay, so this seems a bit tricky because, like if the original set was partitionable, I know the sum is divisible by 2. But if the next set is partitionable, right? If this thing was 3 partitionable instead, the other thing that we need to come up with is 3 partitionable, then you need the sum to be divisible by 3 instead, which is like it's kind of weird, right? Like how would you do this? Seems kind of difficult. Okay, so that's kind of tough. Then I thought to myself, okay, so at the end of the day, what we really just need is, you know, like x to be equals to y to be equals to z, right? And we kind of, you know, me falling back to that intuition of, you know, we kind of really just want to show that you're actually just solving partition, right? So the idea that I had in mind was, hey, if we're really just trying to solve partition, then, you know, maybe we can somehow make these two sets the same somehow, right? And z should just be like some junk. Okay, so now we're getting somewhere. What can we do? Okay, so then I thought to myself about this, and I thought, if x and y, if you know, I want to make this correspondence, right? If I want to say that x, you know, is still going to be x and y is still going to be y, z has to be some made up elements, right? You know, z has to be some stuff that you're adding in, right? So in other words, what I'm saying is that if I try to work along with this intuition, what's going to end up happening? What's inevitable, right? Is that it's going to be, the reduction is going to look like me copying some my elements a1 to an, and then adding some other elements here, right? Then I thought to myself, okay, but if I already know z is going to be by itself, right? Then I could just put a single element there, right? And I know it has to be equals to s and it has to be equals to y, so why not just put s over 2? Right? And I mean, like s over s here is just some of the elements in AI, like, you know, like the elements in AI, right? Okay, does this work? You know, you can't celebrate yet, right? You have to prove it. I mean, okay, does it run in polynomial time? Well, yes. Adding up the items and then dividing by 2 is a polynomial time operation. Then you just put it into a set and you just copy everything over. Seems fine to me. O(n) time. Okay, so that's good. That's fine. Then the next question becomes, all right, so what do I do? How do I prove that it's correct? Right, we do the usual thing, right? We do the usual thing. So we'll say, okay, like, you know, this is our reduction. Our reduction copies the items, and then it just plops in this s over 2 here, which was the sum of, you know, like all the items divided by 2. Okay, so let's say the original set was partitionable. What does that mean? That means, again, that you find yourself in a situation where, let me use a different color. You find yourself in a situation where you have two sets, x and y, right? Again, x and y disjoint, and, you know, and they partition it and they sum, blah blah blah. They sum to the same thing. Okay, so what can we say about the set B here? Well, we know that we can look at this part and we can partition it into the same thing, right? We can partition into x and y, right? And then this item here, we can just put it in some set by itself. And then we call this z, right? Okay, so we did this. Do they sum to the same thing? Well, yes, right? Because this part has to sum to s over 2. This part has to sum to s over 2. And this part obviously is s over 2, right? So all the sets, like, you know, like summation wise are the same thing, right? Cool. So if I could partition the original instance, you know, I could try partition the next instance, right? But okay, so like at this point, you know, like usually what I find in people, and usually what I used to do is, after I do the yes to yes case, right, I start getting excited. I think, oh yes, you know, it's gonna work, right? Like, let's, like, this reduction works. All I have to do is just, like, it's just a formality at this point to prove the no implies no case. You know, like, well, you know, I think it's very obvious. Like, it's very easy to come up with reductions where the maps yes easily, but the no's don't. So you know, I like time and time again, I learned to not celebrate that early. Yeah, so I'm saying, don't get excited now. We get excited later when we've proven that it's correct, right? This assumes that all elements are positive integers, right? For proof 3 from partition to be, no, it doesn't have to be. There's nothing here that requires me to be positive, right? You could sum negative elements, it's fine. I've not required the assumption that anything has to be negative. I mean, I've not used it anywhere. I might use it later on, but I'm, you know, like, for now I haven't. It's a good question. I've not thought about it, but like, I'm pretty sure the answer right as of right now is still no. I didn't really use anything. I think in the next part I might have, or maybe the one after that. But for now, no. Yeah, I mean, if it helps, you can pretend it's positive. I think the next reduction I will need to pretend it's positive. But yeah, but for now, I'm pretty sure the answer is no. Anyway. Okay, so let's move on. Now I'm gonna do the contrapositive thing that I do, like, that I, you know, that I did last time, and, like, you know, time, like, before. So let's do it here now. Let's pretend that we had this set, right? This set that came out of our reduction. So you know, our reduction happened and we came out with a set. And this set happened to be a yes instance. We need to show that it was because, like, this the input to this reduction was also a yes instance, right? That's what the contrapositive thing is trying to say. Like that's the way the ideal works, right? Okay, so we have this set. It came out like this, and we say, hey, assume it can be partitioned, right? So if it can be partitioned, there must be some sets. Let's call it I, j, and k. Okay, such that they partition this guy, and the sum was the same, right? Okay, so the first thing to know, it partitions it. What does that say? That says that S/2 should be somewhere, right? Okay, fine. Let's just put it in K. It doesn't matter where we put it. We could put it in I or J as well, right? You can just shuffle the sets around. It's completely fine. Okay, so the first observation that I made in my thinking process was, let's say S/2 was by itself, right? Can I put other items in it? Like, can I take some of these items here and put it here? Like, in other words, can K steal some of the elements away, right? Because remember, if I move back, right, why did I do this reduction? My intuition was the tripartition problem, right? If I want to solve the two partition problem, should really just, you know, have the same partitions, and Z should just be by itself, right? So we kind of need to execute this intuition. We kind of need to say Z should, like, you know, like this item should only, like, in other words, this guy should only contain S/2, right? So I need to show that, hey, this guy should really only contain S/2. Assume that, so let's assume that it can be tripartitioned, right? Assume that there is a way for you to break into three parts such that if you sum across all the elements, they're always the same thing. Like, I mean, the sum is the same, right? Then the question becomes, hey, can K take any of the items from AI to AN? Well, okay, let's try, right? Let's try and see what happens, right? So okay, so that's my thinking process. Like, can we do it? I don't know. Let's try. Let's throw some items inside, some AIs, maybe, I don't know, like whatever, right? So let's say this set now contains S/2 and some other items. Okay, so the next thing to look at is if, let's say, K did really steal these items, right? What's the value of K here? The value of K here is going to be something, let's say, strictly larger than S/2. Okay, I guess this part I need it to be positive, right? This part here assumes positive integers. So yeah, like, you know, like for the positive part, for the yes to yes part, you don't have to. For this part, yeah, I see why you would need to. So where was I? So right, so the sum here has to be larger than S/2, right? So yes, this part here will assume positivity, right? The sum of the items in K is greater than S/2, and this part here, right? Notice that since we stole some of the items from A, right, I and J can only take the remaining items from A and split them up amongst themselves, right? So whatever was stolen, let's say, is stolen, right? And whatever remaining elements have to be distributed amongst I and J. Okay. Now the difficulty here is that if you had this, right, then the total value of the items in I and J have to, like, you know, if I took all the items in I, sum them up, took all the items in J, sum them up, and added them together, this has to be strictly less than S, right? It has to be, right? Why? Because, you know, some of the items here were taken out, right? And so you take all the remaining items here, you add them together. That's the same thing as adding these items, right? Adding all these items has to be less than S because some of these items were taken away from it, right? Okay, so we know that both of these items are less than S, but we know that they have to be equals, right? We know that these two have to be equals. So since adding the two of these items together summed up to something less than S, each item, each set alone has to sum to something less than S/2 each, right? Now we have an issue because this set sums to something larger than S/2, and these two sets sum to something, oh, sorry, shouldn't put a sum here. And these two sets sum to something less than S/2, right, each. So this guy's less than S/2, this guy's less than S/2, right? That's an issue, right? Because we also, you know, because we assume this is a tripartition, you know, I has to be equals to J and has to be equals to K. But now both our sets I and J are too small, right? What's the intuition behind why it's too small? Because K shouldn't have stolen any elements. K by itself already has a really big element, right? Like this value is so big, you know, like if you put anything else in it, the set just becomes way too large for anything to work, right? So what's the idea here? So I mean, like, that was the idea. So how do we finish the proof, right? So we finish the proof by saying, okay, so it can't be the case that K contains anything else, right? So K can really only contain S/2, right? Now if K can only contain S/2, what does that say? That says that these remaining elements, right, A1 to AN, have to be partitioned amongst I and J, right? They have to be split evenly amongst I and J such that the sum is the same, right? Now, what do we know? We know that if the sums are the same, right? In other words, like I take some items from this set here, they go into J. I take some of these items here, they go into I, right? What do I know? I know that if they can be tripartitioned, right, it must be the case that J is equals to K is equals to I, and I is equals to J, right? So in other words, all these items all sum up to S over 2. And in particular, I is equals to J, and I contains only items from A, J only contains items from A, and both of these guys partition A. That rhymes, kind of, right? So what does that say? That says that we've partitioned it, right? So the intuition carried over, right? So like by padding this element and by tripartitioning it, the same set X and Y that partition the original problem end up helping to partition the new problem, tripartition. Right? So we've argued that it runs in polynomial time. We've argued that it the yes instances of two partition map to the yes instances of tripartition, and we've argued we've argued that if the output of your reduction is a yes instance, right, the input must have been a yes instance as well, right? I know normally at this point I would try to stop and say like any questions because I don't want to move too fast, but I really do want to finish covering the rest at least, right? So post any questions you have in chat, I'll post them on Telegram. I'll answer them when I can. But for now, I'm going to move on to the next question. All right. So the next one is departition. Okay, so the departition, I think like you should think of it as like disjoint partition. Basically, this time you're given two sets, A1 to AN and B1 to BN. Okay, and the idea behind this question is it says, okay, if I have these two sets, right, and they're disjoint from each other, right, the goal here is to output yes. Okay, if and only if you can split this guy into two sets, x1 and y1, like the same way. So you can partition both set A, and you can partition set B. So in other words, if and only if A can be partitioned, okay, and B can be partitioned. Okay, so this one has to be split to x2 and y2. Okay, so in the exam paper that I'm taking this from, okay, the goal here is for you to reduce from reduce from departition to partition. Right? Remember, if I draw this inequality this way, the reduction direction is this way. All right. Okay, so let's do that. So again, my thought process, what was I thinking? All right, you want to do a reduction from departition to partition, right? So what that means is that I'm given two sets, A1 to AN, B1 to BN, sorry, not BN, but let's say BM, right? And my reduction is gonna take these two things and it's going to give me one big set, right, of items. Let's say that, what I want is to combine these two sets into one singular large set, right? Such that if the original was, like this set should be partitionable if and only if both of these in conjunction are partitionable, right? Like both of these can be individually partitioned. Okay, so let's work with that. What are we thinking? The issue here is kind of that, if you kind of need to make these numbers, like these summations, independent somehow, right? Because these two sets are different. Okay, and now when you combine them into the same set somehow, right, you run this risk of having the numbers interfere with each other, right? Like for example, if I just copy pasted the sets, right, like A1 to AN and then like B1 to PM, just put this in one set, right? The yes instances map to the yes instances, right? That's easy, right? Because I know there are two parts here that are the same, right? And I know that there are two parts here that are the same, right? I can just partition this to like X union S, and I can partition this to like Y union T, right? So, and I know, okay, actually this kind of looks like sus, but anyway. But I know the items here, right, sum to the same value as the items here, right? Because I know X sums to the same items as Y, and I know S sums to the same items as T, right? So assuming that both, like if I just copy pasted, right, assuming that the input was partitionable, right, this, constructing this set we don't seem to find fault with this set that we just constructed, right? The issue is the no instances. How do you prove the no instances don't exist, right? Because you could have, for all you know, you could have values where even though you can't partition like these two elements, right? It just so happens that there is a way for you to mix some of the items here with some of the items here, so that the sums work out, right? Like the items from B somehow help the items from A, so that overall they're partitionable, right? So that's a difficulty, right? You can't just copy paste them, which is my thought process. It's like, okay, let's try copy pasting, see what happens. Oh, okay, that doesn't work. Definitely doesn't work. Right? I'm pretty sure like if you try it hard enough, you come up with a counterexample. Okay, so the point is that it's like we definitely don't want this, and the reason why we don't want this is because it's like the items from A interfere with the items from B, right? So fine, what can we do instead? We kind of want to put them in the same set, but we don't want them to interfere, which sounds very contradictory, right? But there is a way to make it happen. There is a way to make it happen. So what I'm gonna do here is that I'm gonna take these items, and again, get a sum out of them, right? So let's just say sum of AIs over here is equals to S. This is always handy. It's always handy. It's like it's the gift that keeps on giving. Okay, what I'm gonna do is I'm going to copy paste A over, right? So A1 to AN comes over. Okay, but when I copy B over, right, I'm not just gonna put B. Like for example, B1, I won't put B1 in the set, right? What I'll put is actually S plus 1 times B1, S plus 2 times B2, so on and so forth, until S plus 1. Anyway, what did I write 2 here? I should have written 1. S plus 1 here, right? And S plus 1 BM. This is what I would try next. I know this looks weird, right? Why would you multiply the sum? Like what good does that do? You might be wondering. Okay. Let's take a slight detour and talk about digits. Okay. So let's say I have two numbers, right? Let's say in base 10, right? So that we're all comfortable here. I have two numbers. Let's say, like I don't know, maybe some sequence of numbers. It doesn't have to be two, right? It could be three numbers. Let's say I have three numbers, right? And the numbers are like 12, 31, let's say 42. Right? Let's say I had three numbers. It can be more, right? But the point is, let's say I had these numbers, right? And I guarantee you, right, that the sum of the numbers on the left side, on the first digit, never hit 10. Right? For the sake of an example, let's say the sum of the numbers on the first digit don't hit 10, right? Will there ever be a carryover into the second digit? Carry forward into the second digit? The answer is no, right? Because these numbers don't hit 10, right? So if I try to do addition this way, it all works out, right? I can just add them individually. It's as if I drew some invisible line between them, right? And then the sum for the first digit is going to be 5. I don't even have to look at, and the second digit, I don't even have to look at the first digit, right? Like the first digit is irrelevant to me because I'm guaranteed that the first digit, right? Like the sum of all the items in the first digit never hit 10. Right? Okay. And in the second digit, I can just do it by itself, right? I just know 1, 3, 4, this is 8. Right? Do I have to worry about carry forward? No, I don't. Right? And I'm trying to get this idea done, but instead of using base 10, I'm using base S plus 1. Right? So intuitively, pictorially, what are we trying to say? We're trying to say that, hey, if you ever took a subset of these items and you added it, right? If you ever took a subset of these items, so let's say I had some subset of items, let's say W, right? W can only hold, so in other words, if it's a subset of items from here, it will be some items from A, right? So maybe like, for example, let's just say, I don't know, AI, AJ, AK, for example, right? And then some other items from B, right? But the items from B will be like S plus 1, let's say like B2, I don't know, S plus 1, B3, so on and so forth, right? Okay, so pictorially, what happens here? Like if we think about this as digit S plus 1, right? If you think about this as base S plus 1, okay, then adding all these items up kind of looks like this, right? It kind of looks like, let me get rid of this. I need space. It kind of looks like this. It kind of looks like AI. I need more space. AI, AJ, AK, right? And then this funny. I mean, at this value it's all 0, right? But when it's B's turn, it becomes B2, BJ, let's say, right, 0, 0. Right? So when you add these numbers up, right, and this is again in base S plus 1, right? So the B2 and BJ are on the next digit, right? AI and AJK are on the first digit, right? B2 and BJ are on the second digit. So when you add these up, right, you know that the final value you're gonna get here is like B2 plus BJ, B2 plus BJ, right? Like in the second digit, and in the first digit, you're going to get AI plus AJ plus AK, right? No interference. Notice how the value of the second digit, right, has no interference from the values of the first digit, right? Why? Because it's S, right? Like in the worst case, you put all the items of A in the first digit, and you would still never get a carryover. I hope that explanation makes sense. That's the idea, right? If the S plus 1 thing doesn't make sense, try to do it for 10 first, right? Try to say, okay, let's say I give you a lot of numbers to add together, right? But I promise you that they'll never hit, they'll never exceed 10, right? So you can see how this separates things, right? If I have two sets of numbers that I want to add together, right, I could just pretend that they were just one big set of numbers, but the first set of numbers is on the first digit, the second set of numbers is on the second digit, right? And as long as I promise that, when I do this addition, there's no carryover, that's good, right? Okay, so we have that idea. Let's finish the proof, right? The proof idea should be like kind of straightforward at this point, right? Because we already have this digiting idea. Okay, so let me put the sets at the bottom. So the original set was A1 to AN, A1 to AN, and then the next set is going to be B1 to BN, right? Okay, assume that this set could be partitioned and this set could be partitioned, right? So in other words, I could get some x1 and some let's not use x2, let's use y1. Assume that you could partition to x1 and y1. You could partition this to x2 and y2. Okay, the question becomes, how do we partition this set, right? Well, okay, well, let's come up with a set. Let's call it W, and I guess another set, what do we call it? Let's call it T. Okay, so this set is going to contain all the items from x1, right? And it's going to contain the corresponding item from y1. But remember, in the set that it's taking from, right? It's not the items from y1 exactly, right? Sorry, not the items from y1. What am I saying? And it's going to take all the items from x2. But the items from x2, remember, because these are b1 to bm, right? We don't have the items b1 to bm. So we need to take every item and we need to multiply with s plus 1. That's what's in the set here, right? B1, B2, B until s plus 1 bn. There we go. Right? So if x2 as a set, right, took items from b1 to bm, right, you need to take the same items, but you have to multiply the s plus 1. That's what's in this set here, right? So okay, good. So w takes items from the set that we constructed. Okay. Now t does the same thing, right? T takes items from y1, union the items from y2, s plus 1. Okay. Well, do they have the same sum? The answer is yes, right? Because if you summed up the items in x1, right, and you sum up the items in y1, these two items are going to sum up to the same value, right? And if you sum up the items from x2, right, it's going to be the same as the sum of the items in y2. Okay. And the thing to note here is that since these two sums are the same, right, we can conclude that the same sum, right, but weighted with an x plus 1 is also the same. Right? Because I mean, it's really the same value. So if you multiply the same value, you're only gonna get the same answer anyway, right? Okay, good. So this means that these two are the same. Okay, so in other words, if the original instance could be partitioned, my output set is also partitionable, right? The next question becomes, hey, what if I couldn't partition it, right? What happens then? Okay, so assume that the original set could not be partitioned, right? Let's see what happens in the output set, this set. So let's pretend for the sake of a contradiction that it could, right? Then what's going to happen is that W here is going to be, again, you can pretend that it's going to be some sum of some items in AI, right? So it's going to be like some of some items in AI plus some sum of items in like BJ or whatever, like that, right? Likewise for T, right, this is just going to be some of the remaining items of AI, let's call it, let's say AI prime. So we know that these two are a partition, right? Plus some other sum of elements from Bj prime, right? Like you can think of it this way, right? Like if W and T are subsets of our output set that kind of partition it, then of course, you know, you can think of them as, did this item come from A or did it come from B, right? It's a very, I think that's a very straightforward observation to make. Okay, so the first thing to note here is this. Let's say that these two were not equals, right? Let's say you could not partition B. So let's say we could not partition B. Right? So that tells you that if you could not partition B, right, that tells you that no matter how hard you try to find a subset, right, of B, right, you know that when you try to, like, you know, like no matter how you take the items and its complement, the difference between them is going to be at least 1. Right? So if the difference between them is going to be at least 1, okay, what is the difference here? The difference here, since this part here that has a difference of at least 1, you know that this part here has a difference of at least s plus 1, right? So what's the intuition here? So now, you know, because by merit of the fact that B is not partitionable, right? No matter how hard you try to find these two subsets, right? The yellow part of the sum, right, causes a difference of at least s plus 1. What about the purple part? Can the purple part make for it somehow, you know, make up for it somehow? You know, we say, okay, you know, there's a difference of s plus 1 or something. Maybe we can find elements from A so that we can offset this difference, right? So that we can deal with it, right? So what I'm saying is that, you know, for all we know, right now, right, T has a value larger than W of at least s plus 1. You know, could T take more items from A to fix this issue, right? Sorry, can W take more items from A to fix this issue? Can W put in more items into its set so that you know, it makes up for this difference, so that they are equals again, right? Because we want them to be equals, right? This is what we want, right? Well, the answer is no, right? Because, you know, in the worst case, right, or in the best case, W can take all the items from A and T takes none of them, right? In which case, you know, W has this and T has this, right? But the difference remains the same, right? Like this is s plus 1, right? So in other words, W is going to be, you know, strictly less than T always, as long as if B is not partitionable, right? If B is not partitionable, this yellow part of the sum, the difference is just too large. The purple part of the sum will not be able to help you in any way. That's the idea, right? I'm really sorry if I'm going too fast, but there's really stuff that I need to cover. So like, if you have questions, post them in chat or Telegram, and I'll answer them when I get to them. Or like, you can watch the video again at like a slower speed if, like, you know, this is all too quick. Let me move on. So, you know, so we said, okay, so what we said was, hey, if we could not partition B, we know it's not possible, right? But the original question, like, you know, like was kind of saying, hey, you know, it should be a no instance if either of the two are not partitionable, right? So in other words, we need to show that, I mean, okay, you could say, hey, but what if B was partitionable, but A was not partitionable, right? So in other words, B could be partitioned, could be, but A cannot, right? Like B partition. You still need to show that we have a no instance, right? Like this reduction doesn't suddenly, you know, happily give us a yes instance for no reason, right? So how do we prove that? Okay, let's think about it. If B could be partitioned, right? Then the idea here is that, hey, we should make these two items the same. We should make these two sets the same, right? Because we know that, okay, so at this point you might be saying, hey, but maybe B could be partitioned and we should not make these two things the same thing, right? But the same idea still holds from the previous part. If we cannot make these two sums the same, right? This difference of s plus 1 is too big for us, right? So you know, if B could be partitioned and you don't make them the same argument as I've made, you know, as I've laid out just now holds, right? This difference becomes this difference is at least 1. So then the yellow part, right, the entire yellow part is at least s plus 1 different, right? And then, you know, the purple part cannot make up for it. So okay, fine. So let's say, so now we understand that, hey, if I don't make these two sums the same, I'm screwed, right? Okay, what happens if I make these two sums the same? Am I still screwed? Right? So fine, let's make the two sums the same. Now we assume that B could be partitioned. So, okay, you know, why not? So the yellow part is the same now and they cancel out, right? So the only difference between W and T now is whatever difference, you know, like these two parts have, the purple part, which is uninvolved, which is unrelated to the yellow part, right? Okay, so then if you look at the purple part and you say, hey, if these two things sum to the same thing, right? And these two things like, took items from A, but I assume that A could not be partitioned, then it's a contradiction, right? Because I've literally split up the items from A, like amongst myself, right? And these two sum to the same thing, but I also assume that A could not be partitioned. Well, that's a direct contradiction, right, to our assumption, right? So in other words, what I'm saying is that, hey, if B could not be partitioned, our output instance is definitely not partitionable, right? If A could not be partitioned, still not partitionable, right? So all this goes to show that, hey, like doing this idea of like taking this set and then doing this digit trick kind of like gives us the correct reduction. Okay, good. So what can we conclude? We can conclude that this thing runs in, it definitely runs in polynomial time. So we can conclude that this is a polynomial time reduction, right? So in other words, we've correctly, proven that D partition reduces to 2 partition. All right. Now I think the last question in the exam actually asks you to show this. It asks you to show reduce D partition to 3 partition. Okay, and if you notice, the box is kind of small, right? Because the answer is you're not supposed to explicitly give a reduction, right? You have a reduction from D partition to 2 partition, right? You have a reduction from 2 partition to 3 partition. So all you have to answer is apply the algorithm from D partition to 2 partition, then apply the algorithm from 2 partition to 3 partition, right? So like in other words, take the first algorithm, right? It takes the 2 sets and outputs a single set, right? And then take the sorry, did they ask for that? What did they ask for? I don't remember. No, we reduced. Yeah, we reduced 2 partition and 3 partition. Yeah, that's correct. That's correct. So you take this one set, right, and then you take these 2 sets and you output one set, right? Then you take these 2 sets, this one set, and you output another set, right? That's the full reduction. Yeah, I was right. Okay. So that concludes that. Now let me quickly, hopefully in something like 8 minutes, cover the last thing that I want to cover for today. Okay, so I want to talk about approximating MIS. So MIS, if you've been out of the loop, MIS, the goal here is to find a maximal set of vertices such that they don't share an edge. Okay. Now this is a difficult problem, right? We've harped on in class time and time again. MIS is difficult. Like we don't know a polynomial time solution for solving it. Like, if you do, you're a genius. You deserve $1 million, that sort of thing, right? Today we're gonna try to approximate this. We're gonna try to come up with an algorithm that kind of like hopefully does pretty well. Okay, and like when I say does pretty well in terms of approximations, it's actually not really good, because MIS is a very difficult problem. It's a D approximation, where D is equals to the max degree of the graph. Okay, we're gonna go for something a bit easier first. So last semester they did a D+1 approx, and during my semester when I took it, they did a D approx. Okay, so first thing to note, this is a maximization problem. If I'm coming up with a D+1 approx, right, it means that the output of my solution has to be at least, right? I cannot stress this enough. At least, okay, 1 over D+1 of the optimal solution. Okay, because like when we did vertex cover, right, we didn't want to find too big of a set, right? So the set cannot be too big. So when I say 2 approx, it means that, hey, if the optimal size was, like let's say OPT, right, the size of my vertex cover should be at most 2 times OPT, right? Today I'm doing the opposite thing, right? I'm trying to maximize, right? Like the best thing to do is to maximize. So I want to guarantee my solution is at least some value. Okay, so when I say it's a D+1 approx, what I'm saying is that it has to be at least 1 over D+1, right? And like, bit of a short background into this whole thing. When this came out during my semester, like I said, right, it was not a D+1 approx, it was a D approx, which is correct, by the way. It's a D, like I'm about to show you a D approx algorithm, right? I didn't solve it during my exam. So I didn't bother with the question years later. I only solved it yesterday. Okay. And this was actually the reason why I keep telling people I don't know how to do approximation algorithms, is because that question really killed me during my finals. and I never went back to it. So this was really like my PTSD question. All right. But I'm solving it for you guys. So let me show you the thought process, right? So where was I? Okay, so we'll do a D+1 approximation first. Then we'll see, hey, the proof is actually not really great, and we'll try to improve it. Okay, so let's work with this. Now that okay, first things first, come with the algorithm, right? And the algorithm is really simple. It's really just 3 lines. Okay, what you're gonna do is you're just gonna while there are still vertices, Okay, what you're gonna do is really simple. You're just gonna take some vertex, add let's call this vertex V. Add into set S. Okay, delete V from P. In other words, your set of vertices, as well as all of its neighbors. Okay, keep doing this until there are no more vertices. After that, what you do is just return set S. The algorithm is really that simple. That's all there is to it. Okay, it's like what, 4 lines at most? Okay, I mean, honestly speaking, this deletion is not that simple, right? but yeah. Okay, so but that's the idea. That's the main idea. Okay, so let's talk about this. How do we show it's a D approx, right? Sorry, how do we show it's a D+1 approx? Okay, I'm really sorry, I'm running over time, but like this is the like you can watch the recording if you have to go. Okay, so we have a D approx here. We want to show a D+1 approx. So the first, when I solved it yesterday, right, I still remember this. The first thing that I asked myself was, okay, so we know that we keep adding vertices into the set, right? And the more we add, it's the better we get, right? Like, because okay, the first thing I ask is S an independent set? The answer is yes, it is an independent set, right? Why? Could you ever add 2 vertices that have an edge to each other? The answer is no, because the moment you add something into the set, right, you delete all of its neighbors. In other words, they're gone from consideration, right? Like you can't you just can't get it, right? Okay, fine. So then the question becomes, okay, I know this, right? Now the thing is that you have to remember that since we're trying to maximize, right, the longer our algorithm runs, the better it is, right? That was the thought process that I had. It's like, okay, so every time I run one more iteration, my proposed independent set size, right, grows by 1. That's good. That's good for us, right? Because we want to do more, right? And the longer this thing runs, the better it is, right? So then the question becomes, okay, is there a limit to how good this is? Like how at least how much of this quote unquote goodness can I guarantee for us, right? So let's think about it. What am I doing every time? So let's say my set size is K, right? Okay, so every time I add an element, right, how many vertices get deleted, right? So I note here that every time I add I add like some V into S, right? Every time I do this, right, I need to delete V plus 1, not V, sorry, D plus 1 vertices from the, delete D plus 1 vertices from the graph, right? Okay, and how long does this algorithm run for? Well, it has to, I mean, okay, when I say delete D plus 1, I mean like at most D plus 1, right? Because the max degree is at most D, right? So since the max degree is at most D, you have D neighbors in yourself to remove from the graph. So you delete at most D plus 1 vertices. And you need to keep doing this until you stop, right? So what does that tell you? And remember here, right? The size of the set here is the number of iterations that we're running, right? So the number of iterations that we run times the number of vertices that we delete, right, has to be at least the number of vertices that we have, right? If not, the algorithm doesn't stop, right? So we know that, okay, so this is kind of like a best case scenario, right? In the best case scenario, well, best or worst, depending on how you view it, right? But like at least, right, like the most our algorithm can delete at every iteration is D plus 1. Okay, And we know that after k iterations, we've deleted k times d plus 1 vertices from the graph, right? So before our algorithm stops, what's going to happen is that you need to, you need to delete all the vertices from the graph. So in other words, k times d plus 1 has to be at least v, right? But what do we know about the MIS? What do we know about the MIS? Well, the maximal independent set, in the best case, can only contain all the vertices, right? So in other words, what I'm saying is that k, I mean, well, like if you don't use k, you can use s. S is really just s times d plus 1, is really just at least the MIS size, right? I mean, okay, I hope this is clear, right? It's like you can't, like MIS is a set of vertices. You can't have you can't have a set of vertices more than the vertices you already had that are in the graph, right? You can't just pull them out of thin air, right? So this gives me that S is at least MIS over D plus 1. Does that make sense? I mean, what I meant to say here was OPT, but like same thing. OPT. Okay, so if you're a student from like last year, this is how you solve it. I mean, last semester, sorry. Now, if you're a student from my year, right, this is not enough because they want you to show a D approximation, not a D plus 1 approximation. All right. So in other words, this is not good enough, right? Because notice, right, that that OPT over D is actually bigger than OPT over D plus 1. Right, because it's like you're dividing by a smaller value, so your reduction is smaller, right? Your reduction in like value is smaller. D is the max degree of the graph. D is the max degree of the graph. Remember, you're counting neighbors, right? That's why D is here. It's like if you delete yourself and all of your neighbors, and in the worst case, I mean, like in the most extreme case, you deleting yourself and you deleting all your neighbors is deleting at most D plus 1. No, it's not a constant. It's not a constant. Side remark, you can't it's very hard to get an approximation of independent set which doesn't take into account the degree. Let me give you some intuition, which actually ties into how I'm about to solve the D case, right? So I was mentioning how if you were last semester student, you would have solved it already, right? This is the solution, just D plus 1, that's how you get it. But if you're a student from my semester, there's a lot more work involved because they wanted a D approx, and that proof only shows a D plus 1. It doesn't show a D approx. Okay. So at this point, right? I like remember how Govin posted in the chat saying, "Oh, that's wrong. It's supposed to be D plus 1. D plus 1 very important, right?" Then I thought to myself, okay, but if D plus 1 is important, right, you must have been able to come up with a graph that shows D plus 1, right? So I was thinking to myself, okay, so what kind of graph is the worst possible case? Let's say I have a star graph. So over here in this example of my star graph, right, the degree is 1, 2, 3, 4, 5, 6, 7, right? It's 7. Okay, so here for this example, right, D is 7, right? And I know that the MIS, let me color it in yellow, looks like this, right? But it's not a constant. But I also know that the worst possible node that my algorithm could pick, right? Like if I was being, like really unlucky, would be the one in the center, right? The moment it picks the one in the center, right, all of the other nodes are gone. Okay, so but if you do this, right, like which I'm very convinced is the quote unquote the worst possible thing that could happen to you, right? Like in this algorithm, it's this only gives a D approximation. It doesn't give a D plus 1 approximation, right? So which is why when Govin said, hey, the plus 1 is very important, I was thinking to myself, yeah, but how do you hit that plus 1? If you're saying it's important, you must have a graph that shows the D plus 1, right? But this only shows D, right? This only shows, hey, the worst your algorithm can do is by a factor of D, not D plus 1, right? And then I was thinking to myself, but how do you show D plus 1? You can't, right? Because like no matter how else I draw my edges, like this is really just it. Like if I draw any edges any elsewhere, it only makes the MIS smaller. And if it makes the MIS smaller, it makes my approx better, right? You want to make the approx the MIS as large as possible and your algorithm's approximation as small as possible. And the star graph is the only way I can think about like the maximum possible distance, right? So it kind of told me, okay, D is possible, which means that the question during my exam was not wrong. Means the plus 1 is not important. Like we could actually show D. In other words, the proof that I just showed you is not the best proof, right? Like so let me show you the best proof. Okay, so the way that we're gonna do it, same algorithm. We're trying to prove for the same algorithm, right? So So the way we'll try to do this is to say, okay, so let's collect the vertices, right? So let's say the vertices that our algorithm collected, let's call them v1 to, I don't know, vk. K is the size of our set, right? So in other words, set S is k. Okay. Now what I'm going to do is I'm going to define something called GI. Okay, GI is basically the set of vertices, so like vi and all neighbors of vi. Neighbors of vi. So that's what's in this set. Okay. Now, if so, in other words, like if you try to draw the graph like this, right? The intuition here is that each of these GIs is a subgraph of the original graph, and they kind of look like stars, right? So like maybe vertex 1 looks like this, vertex 2 looks like this, you know, sort of kind of like that, and like vertex, I don't know, they could share, right? It's fine. It's very possible. Like they could share endpoints. It's fine. Like this, for example. Right? But the point is that you have like all these, you suddenly look at the graph as like all these stars that you have. Okay. So I want to use this to finish off the proof. Okay. So and we know that and we're arguing that, okay, since our graph keeps adding vertices until it can't anymore, right? If this is the case, every vertex, right? Every vertex, blah, 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 for all v in big V, right? There exists some star that it must be a part of, such that v is inside of GI. So this is just a formal way of saying, since we keep adding vertices until we cannot anymore, right? If you just pick out any vertex in the graph, right? I guarantee you it's in someone's star. It has to be in someone's star, right? Because if let's say it wasn't, right? Pretend it wasn't in someone's star, then I could have just added it into a set by added it into set S, right? So it has to be in the star. It's either on the fringe of the star or the center of the star. Either one of them. It can't be neither, right? Because if it wasn't, we would be able to end the set S. Okay. Okay, so this is good. I know that everything is in. I know everything is in the star, right? So let's finish the proof. So the proof says something along. Let's say OPT is the set of let's say OPT, right, is the set of like the maximal set of like the independent set, right? The best one, the best independent set. So this is a set of vertices, right? Since I know this is a set of vertices, I can just decompose it, right? It's a disjoint union from I is equals to 1 to k of gk, gi intersected with OPT. Right? So this is saying that, okay, like I have this independent set. I know that each of these guys belong in some stars, right? So viewing them together is the same as taking them in their respective stars and summing them up, like unioning them together, right? And it's a disjoint union, right? So then what can I say? I can say that the size of OPT, right, is the same as the sum of the size of GI intersected with OPT. Right? From I is equals to 1 to k. Okay, all this is saying is, let me just cut up the optimal set into its respective stars. Okay, and then the question becomes, well, how good can this go, right? I know that GI, like I know that each of these guys have a max degree of D, right? So the best that I can, the most amount of intersection I can have with OPT is at most D. Not D plus 1, but D. It can't be D plus 1 because remember, our stars, right? The stars that we made, which look like this, right? Okay, have D outgoing edges. Okay. So when I say that each star intersector is OPT is a size at most D, right? Not D plus 1. The reason why it's not D plus 1 is because you cannot contain the whole star. You can only contain the fringes or the center, right? And note that since it's a star, right, the most intersections you can make is when when the optimal is at the fringe, right? Like these are all the optimal vertices, and this is not, right? This one is not part of it, right? So it can't be D plus 1. It can only be the fringes, right? So G intersect OPT is at most D, but D is again the max degree of the graph, right? So let's plug that in here. Let's plug that in here, right? So this tells me that this is at most sum of I is equals to 1 to k, right? D, right? Which is equals to KD. So what can we conclude? We can conclude that OPT, right, is at most KD, which means that when, again, this is the size of our set, right? So K, which is the size of the set, is at least OPT over D. So we've removed the D factor, right? So what's the intuition here? The intuition here was really, if you look at this graph, right, you sort of like think about how, like what's the worst, what's like how bad can my algorithm screw up? Well, my algorithm screws up if like, I look at all these stars and it keeps picking the center, when you could have picked the fringes, right? You pick the side on the side of the stars, right? Then somehow translate that intuition into a proof, like, like get this set and say, okay, I have all these stars, the fringe, like, I'm gonna argue that like the best things to do is to pick the items on the fringe, right? And I can break this optimal set of indices of vertices into only the ones on the fringe. Then I would say, hey, okay, in my worst case, right, for every star, right, my algorithm always screws up no matter what, right? And even then, when it screws up no matter what, right, like you only lose by a factor of D. Well, actually, D is pretty bad because if D was large, you have a really bad independent set, right? Like if the graph was a star graph, then you would turn a really small independent set, maybe size 1, for example, which is really useless. All right. So that concludes. I've actually run really far over time. I'm really sorry. So that kind of concludes today's class, and today's like the last class of the semester. I've actually not. I mean, I've not met most of you guys in person. So Anyway, I was hoping to say that like I hope you guys had fun in class. I hope you guys learned a few things, and I hope you guys. I mean, more importantly, I hope you guys had fun. So yeah, I guess I'll see you guys if or whenever I see you. If you still have questions, you're still free to send them on chat or email them to me. I'll answer them when I can. But if not, that's pretty much it. And one last thing. So if you guys did enjoy the class, and can find the time, do feel free to drop by the feedback form and fill out the teaching feedback for me. I'll remind you, if you guys are busy now, that's fine. I'll remind you guys again in a few days' time in case you feel like doing it. It's fine if you don't, but I would really appreciate it if like you guys did. But if not, yeah, that's all I have to say for the semester. See you guys if I see you guys sometime. No worries. I'll post the link to the teaching feedback again later in case you guys need it. Like I'll post it after this class. Yeah. Bye bye. No worries.